All right, so again, the paper that we're solving here is October-November 2021, paper 42. Okay, and what we have over here is question number 1. Radium is a group 2 element. The predicted lattice energy of radium sulfide is negative 2612 kilojoules per mole. Define the lattice enthalpy. So again, since they're asking for the standard lattice enthalpy over here, we're going to say it is the energy released. Okay, or you can say the enthalpy change, but it's always exothermic. So you can say energy released, okay, when 1 mole of a solid lattice, okay, is formed from its constituent gaseous ions. Under standard conditions. Okay. All right. And obviously over here, for lattice enthalpy, we're always talking about ionic lattices. All right. Some data relating to radium and sulfur are listed. Select relevant data from this list for use in your answers to parts B to E. Write an equation for the process corresponding to the second electron affinity of sulfur. Include state symbols. So for the second electron affinity of sulfur, we have over here second electron affinity of sulfur, we're making S2 minus ions, okay, from S1 minus ions. Remember, electron affinity is for gaining electrons, right, to form S2 minus. And again, for electron affinity is going to be gaseous ions. Okay, so those are your state symbols. Sulfur exists as S8 molecules in the solid state. Use the data in this question to calculate the enthalpy change for the reaction sulfur solid to gaseous sulfur atoms. Okay, so what we have is we have S8 forming 8S gaseous. Okay, they want to find the enthalpy change for this reaction. So let's call that X. Now, what data in the table can we use to relate these over here? What data in the table can we use to relate these over here? They've given us the enthalpy change for the formation of sulfide ions from its constituent element, right? They've given us the enthalpy change for the formation of sulfide ions. So let's say over here I have sulfide ions, right? They've given me this data here. We have 8 times the formation of sulfide ions. Sulfide ions, here we're making 8 moles of them. Here we just have 1 mole. So that's 8 times plus 555. And what enthalpy change relates sulfur atoms to sulfide ions? What are these enthalpy changes here? This is the sulfur atoms are gaining electrons. So these are the electron affinities of sulfur, right? And we have 8 moles of atoms. So we have 8 times the first electron affinity plus 8 times the second electron affinity. So now we have a Hess cycle here. What we can say is that either I can first atomize the sulfur and then I can add electrons to it, right? Or I can go directly from molecular sulfur to forming the anions. Okay. So what I have over here is I have X plus 8 times negative 200 plus 8 times 532 is equal to 8 times 555. So what is that enthalpy change over here? So over here, X would come out to positive 1784 kilojoules per mole. Okay. So we have plus 1784. All right. This enthalpy change over here is 8 times the atomization of sulfur, in case anyone's wondering. Okay. So the atomization of sulfur will be just this divided by 8. Okay. You're forming 8 moles of gaseous atoms from the element in its standard state. Calculate the standard enthalpy change of formation of radium sulfide. So what we have here is, again, we have radium sulfide. So we have radium plus sulfur, right? And radium sulfide over here is Ra S. So we have 1 over 8 S8. So we have to calculate this delta H of formation, right? To form the solid from the constituent elements. Now, the first thing we can either do that, or we can go first to making the gaseous atoms, or the gaseous ions, sorry. So that would be Ra2 plus gaseous plus S2 minus gaseous. And then we can convert those ions. We can convert those ions to the solid lattice. That would be the lattice enthalpy. So either we can take the direct route. So we start with elements and go directly to the ionic lattice. That's delta H of formation. Or we can first start with the elements, make the gaseous ions, and then convert the gaseous ions to the solid lattice over here. So what we have over here is, if you look at the data, right, they've given the lattice energy is negative 2612, right? So let's write that down. The lattice energy is negative 2612 kilojoules per mole. I'm not writing the units here. Okay, you have negative 2612, right? Delta H formation is what we have to find, so we don't know that. And they've also told us this. We can go directly from radium solid to radium gaseous ions, right? That is the atomization of radium plus the first ionization energy plus the second ionization energy. That's positive 1619. That entire process to go directly from radium solid to radium 2 plus gaseous ions is 1619. And then they've also told us that we can go directly from sulfur solid to sulfide ions. That is the formation of sulfide. That is plus 555. Okay. So if you go directly from sulfur solid to form 1 mole of sulfide ions, right, that is the formation of sulfide ions, that is 555. So this is the formation of radium 2 plus gaseous ions from the constituent elements, and this is the formation of sulfide ions from the constituent elements. Okay, so what we have here is, we can say 1619 plus 555 minus 2612, that's the indirect route, right? This is equal to the delta H formation. So what does X come out to? Here X comes out to negative 438 kilojoules per mole. So that's our answer. State the two major factors that affect the numerical value of a lattice energy. Okay, the ionic charges and the ionic radii, right, or the size of the ions. For each factor you have identified in E part 1, state whether it tends to make the lattice energy of radium sulfide more or less exothermic than that of sodium chloride. So we have to look at each of these factors individually. Okay, in radium sulfide we have Ra2 plus and S2 minus, and sodium chloride we have Na plus and Cl minus. So they're saying first let's look at the size. If you look at the size, if you look at the ionic radius, right, if you look at the ionic radius, right, if you were just looking at the ionic radius, which of these would be more exothermic? If you're just looking at the ionic radius, you have to look at them individually, right? Each of them, for each of the factors, whether it tends to make the lattice energy more or less exothermic. So if you're just looking at the radius, right, if you're looking at just the radius, Ra2 plus is much larger than Na plus. Ra2 plus is much larger than Na plus, right? So in this particular case, right, when you're looking at radius, it would make the delta H lattice. It would make delta H lattice of RAS less exothermic, right? And the reason why is because the ions in RAS are larger. Okay, remember over here, sulfide ions are also larger than chloride ions. They have the same number of electrons, but chloride has a greater nuclear charge. Okay, from AS chemistry, if you guys remember, right? Nuclear charge is increasing, but the number of electrons is the same. They're isoelectronic. So chloride is actually large. Chloride is also smaller, and Na plus is also smaller. So both the ion and sodium chloride are smaller. So you'd expect RAS to be less exothermic. You have larger ions. But if you look at the charges, what's the effect of the charges? Right? For the charges, you would expect it to be delta H lattice of radium sulfide would be more exothermic. Right? Since both the ions have a greater charge. Since the ions have a greater charge. Okay. The lattice energies of sodium chloride and radium sulfide are minus 771 for NaCl and negative 2612 for radium sulfide. So what's the dominant factor over here? The dominant factor over here based on these two factors is the, even though the radium and sulfide are larger, it's still much more exothermic because they have a much greater charge. So over here, the ionic charge is the dominant factor. Ionic charge, right? Since the delta H lattice of RAS is more exothermic. All right, the next question that we have here is question number 2. Ethoxyethane can dissolve both in water and in octanol. The expression and numerical value for the partition coefficient of ethoxyethane between water and octanol are given. Water and octanol are immiscible. Okay. So normally if they say between water and octanol, right? Here they've given octanol in the numerator and water in the denominator. But again, usually when they say a ratio between A and B, A should be in the numerator and B in the denominator. So the way they phrased it, I would actually put water in the numerator and octanol in the denominator if they asked me to calculate it. But that's fine. Okay, it's a more technical thing. It's more like a wording thing. But this is between octanol and water. Okay, for ethoxyethane. In an experiment, octanol at 20 degrees Celsius is added to a solution of ethoxyethane in water at 20 degrees Celsius. The mixture is analyzed immediately, okay, and a value of Kpc is calculated. The calculation is performed correctly, but the value calculated is 5.625, which is lesser than the 6.76. Now they've done the calculation correctly. So what do you think the problem was over here? Why are they getting a lesser value over here than you should be getting? By definition, the partition coefficient is the ratio of the concentrations at equilibrium. Now, because they've done the calculation immediately, you haven't allowed it to reach equilibrium. You haven't allowed it to reach equilibrium. Okay. So, equilibrium has not been reached. Okay. Equilibrium has not been reached. Okay. Because this value of 6.76 would be obtained once equilibrium was reached. Again, by definition, the partition coefficient is the ratio of the concentration of a solute in two immiscible solvents at equilibrium. Now, when you mix them together, the solute is moving from between the two solvents, okay? But you have to allow it to reach equilibrium. In other words, you have to allow it to reach concentrations. It has to reach constant concentration in both solvents before you calculate the Kpc. They calculate the Kpc immediately, so they didn't let that equilibrium reach, okay? So over here, equilibrium has not been reached. And the value that we're getting is lesser than the expected value, which means that the concentration is too low in either octanol, so the numerator is lesser, or we can say that the concentration is too high in water. And the reason, so we can say over here because, and over here we can also say that, right, the concentration of ethoxyethane, okay, is in water is too high, okay, is too high, or we can say it's too low in octanol is too low. So you're getting a value that's lesser than expected. That's why. A second experiment is performed and the value of Kpc is found to be 6.76. The concentration of ethoxyethane in the octane 1-ol layer is 7.62 grams per decimeter cube. Calculate the concentration in grams per decimeter cube of ethoxyethane in the aqueous layer. Okay. Now, what we have is we have the KPC over here, right? We have KPC is equal to the concentration of ethoxyethane, right? C2H5, O C2H5 in octane 1-ol, right? Divided by the concentration in water, right? Or aqueous. And this is the KPC over here is 6.76, right? And this is equal to the concentration in octane 1-ol, which is 7.62, divided by the concentration in water, which is what we have to calculate. So X is equal to 7.62 divided by 6.76. So here the concentration comes out to 1.13 grams per decimeter cube. Again, you don't have to convert this to moles per decimeter cube as long as the units in the numerator and the denominator are the same, since you're just taking a ratio. All right. 100 centimeter cube of the octane 1-ol layer is taken and shaken with 100 cm cube of water. Calculate the maximum amount in moles of ethoxyethane that can be extracted into the water. Now, over here, what you have is they've given you the octane 1-ol layer ki concentration, right? That's 7.62 grams per decimeter cube, right? So we know that the concentration of this guy in octane 1-ol, okay, in octane 1-ol is equal to 7.62 grams per decimeter cube. So then over here, if I have 100 cm cube of octane 1-ol, what's the mass that I have of the solute initially, right? Can I say that the mass over here in a thousand cm cube, I would have 7.62 grams. So in 100 cm cube, what's the mass that I have? Because I have the same concentration, right? So the mass over here would be 0.762 grams. Okay, so that's the mass that I have. That's the mass of ethoxyethane that I have in the layer over here, right? In the octane 1-ol layer. Now, we want to figure out how much can be extracted into the water. So let's say that in water, right? Let's say that in water, the mass extracted is equal to X grams. Let's say that the mass extracted is equal to X grams. So then in octane 1-ol, what's the mass that's left after we do the extraction? Is equal to 0.762 minus X, right? So can I say over here that the KPC that I have is equal to the mass of the solute, right? Is the mass, or rather the concentration in octane 1-ol divided by the concentration in water, right? I'm not writing the whole thing here, right? But I know that the concentration in octane 1-ol is, I have 0.762 minus X grams in octane 1-ol, and I have 100 cm cube of octane 1-ol, right? And what I have is, I have X grams in water and I have 100 cm cube of water. So this simply cancels out, and this is equal to the partition coefficient, that is 6.76. So I can say over here that 6.76x is equal to 0.762 minus x. So what I get over here is 7.76x is equal to 0.762. So what does x come out to? In this particular case, since the volumes are the same, right? When you find the concentration is mass per unit, in this case we're using mass per unit volume, we're doing grams per centimeter cube. As long as the units are the same in the numerator and the denominator, it doesn't matter. Okay, so what I'm doing is I'm dividing the mass by the volume to find the concentration in octane 1-ol and the concentration in water. But since the volumes are the same, the volumes cancel each other out. So in this case, the mass ratio is the same as the concentration ratio. Okay. And here the mass comes out to 0.0982 grams. Okay. So then we want to figure out the number of moles. We want to figure out the number of moles that we would have. Number of moles is equal to mass divided by the molar mass. The mass that we have is 0.0982 divided by the molar mass. The molar mass of C2H5O C2H5. So C2H5 over here is 24 plus 5, 29 times 2, 58 plus 16. So that's 74. So what's the number of moles that we would have in the aqueous layer? So over here we get 0.00133 moles. Now I'll repeat what we just did over here, okay? Okay, this is our answer here. Let me repeat what we did over here. They told us that we had this octane 1-ol layer and we had 100 cm cube. And we shook it with water and we extracted some of the ethoxyethane out of the octane 1-ol layer. Now we first need to figure out how much did we actually have in this layer initially before we can find out how much was extracted. So how we figure out how much was left is they had already told us that this was the concentration that we had in the octane 1-ol layer. This was mentioned in the question. So we can figure out if this is the concentration in grams per decimeter cube in 100 cm cube, right? What's the mass I would have? If I have 7.62 grams in a decimeter cube, that's 1000 cm cube, I would have 1/10 the mass in 100 cm cube. So I figured out how much mass I had initially in the octane 1-ol layer, right? Once I shook it with water, we want to figure out the number of moles that were extracted in water, right? We can first figure out the mass that was extracted in water. We know that x grams was extracted. We don't know how much that is. Agar x grams extract ho gaye pani mein, to initial 0.762 minus x reh gaye were left in the octane 1-ol. So now we have the mass left in the octane 1-ol and the mass extracted into water, right? So if we divide those masses by their volumes of the respective solutions, we get the concentrations, and the ratio of the concentrations is the partition coefficient. So we can figure out the mass that was extracted in water by using the partition coefficient. Okay, and then therefore we can figure out the number of moles. An aqueous solution of lead-2 nitrate is mixed with an aqueous solution of sodium iodide. A yellow precipitate of lead-2 iodide is formed and filtered out, leaving solution X. The concentration of lead-2 plus in solution X is 5.68 times 10 to the power of negative 3 moles per decimeter cube. The concentration of iodide is 4.20 times 10 to the power of negative 4 moles per decimeter cube. Use these data to calculate the value of the solubility product of lead-2 iodide and state the units of KSP. So we want to find the KSP of lead-2 iodide. So first of all, let's write that down. Lead-2 iodide would have this formula, PbI2, right? And we would have Pb2 plus and 2I minus, right? And this, the solubility product over here would be KSP is equal to the concentration of lead-2 plus times the concentration of iodide squared. Now for the solubility product, we have a saturated solution, and that's exactly what we formed here. When we mixed lead-2 nitrate and sodium iodide together, a precipitate formed, meaning that we had too much lead and too much iodide. So we had a saturated solution form, and then saturated solution ke addition mein we also made a precipitate. So we took the precipitate out and we were left with a solution X. Okay, that solution X was a saturated solution. Okay, and they've given us the concentrations in the saturated solution. So can I find KSP using the concentrations given to us? Right, my KSP over here is the concentration of lead, that's 5.68 times 10 to the power of negative 3, right? And that's the concentration of lead multiplied by the concentration of iodide squared. So what is that equal to? So here we get 1.00 times 10 to the power of negative 9. So we have 1.00 times 10 to the power of negative 9, and the units over here are concentration times concentration squared. So that will be concentration cube. So that's mole cube dm to the power of minus 9. Why we have a saturated solution is this. When you had lead to nitrate and sodium iodide mixed together, what happened was that they mixed together and they formed a precipitate, which means that there was more lead to iodide present than you could have in a saturated solution, right? That's why we saw precipitate. You had more than the solution could handle. You had more lead to iodide present than could dissolve in water. Yani ki the maximum amount had dissolved, and the remaining had precipitated. We just removed the precipitated, so we had a solution just kind of maximum amount remained dissolved. So therefore we had a saturated solution. Okay, and KSP is only applicable for saturated solutions. Potassium iodide is very soluble in water. Describe and explain what is seen if a few drops of saturated potassium iodide solutions are added to a portion of solution X. So solution X is a saturated solution. If I add potassium iodide to this solution, I'll increase the iodide concentration. What will happen to the equilibrium over here? If I increase the iodide concentration here, the equilibrium will shift to the left. So if the equilibrium shifts to the left, what will form? What will form over here? Right? The yellow precipitate will form. So the observation over here will be that you're going to see yellow precipitate forming. Okay? Yellow precipitate forming. Right? And this effect is known as due to the common ion effect. They've given it in the question, right? That we have a yellow precipitate here. A yellow precipitate of lead to iodide is formed. Okay. So we have the common ion effect, right? Which means that the common ion over here is obviously iodide, right? That ion is common to the lead to iodide solution as well as the potassium iodide solution, right? And what's happening here is that the concentration of iodide increases, therefore the equilibrium shifts to the left. All right, the next question that we have here is question number 3. Pure water is a very poor conductor of electricity. However, when hydrogen chloride gas is dissolved in water, ions are formed and a current flows during electrolysis. So because you have ions present, it's an aqueous solution that becomes a good conductor of electricity. The overall change after electrolysis is that hydrogen chloride gas is converted into hydrogen and chlorine. So there's electrolysis of HCl. When a current of 3.10 amperes is passed through the solution for Y minutes, okay, we don't know the time, 351 centimeter cube of chlorine are produced at the anode. Calculate the number of chlorine molecules present during the electrolysis. So first of all, let's calculate the number of moles. For any gas, we know that the volume in centimeter cube is the number of moles times 24,000. Or you can convert this to decimeter cube and say number of moles times 24, right? Same thing. So we have 300, the number of moles is simply the volume divided by 24,000. So how many moles do we have of chlorine molecules? What's the number of moles here? The number of moles that we get is 0.0146 moles, right? So then we want to find the total number of chlorine molecules. So the number of chlorine molecules is the number of moles times Avogadro's number, right? If 1 mole has 6.02 times 10 to the power of 23, how much does this many moles have? So if we just multiply this, what do we get? You get 8.80 times 10 to the power of 21 molecules of chlorine. Okay. Calculate the total number of electrons transferred to produce this number of chlorine molecules. So if we look at the half equation, we have Cl minus forming Cl2 and obviously releasing electrons. And if you balance this, you have 2 of these and therefore 2 electrons. So for every 1 chlorine molecule, right, 2 electrons are produced. So then can I say that the total number of electrons will be twice as many? The total number of electrons will be twice as many. For every 1 chlorine molecule, 2 electrons are released. The total number of electrons will be 8.80 times 10 to the power of 21 times 2. So this is equal to, this will come out to 1.76 times 10 to the power of 22 electrons. Okay. Calculate the quantity in charge in coulombs of the total number of electrons. Now, one electron has a charge of 1.6 times 10 to the power of negative 19 coulombs. So if I had 1.76 times 10 to the power of 22 electrons, what would the charge be? So Q is equal to 1.76 times 10 to the power of 22 times 1.6 times 10 to the power of negative 19. So this value over here comes out to 2820 coulombs. Okay. Calculate the time y in minutes for which the current flows, right? So what we have over here is we have Q is equal to IT, right? We've calculated Q, that was 2820. The current they had given to us in the question as 3.1 amperes, right? So we have 3.1 amperes times the time in minutes. So let's say time in minutes over here, let's call that Y times 60, because this equation is for time in seconds, right? So then, right, what is Y equal to? Don't use the rounded value here. Use the answer key. So we have 2817, I think. 2817 coulombs here. So what does Y come out to over here? Okay, so over here Y comes out to 15.1 minutes. Okay. The standard entropies of 3 species are given in the table. Calculate the standard entropy change for this reaction. Now we know that the standard entropy change is products minus reactants, right? The standard entropies of the products minus the reactants. So here the entropy of the products are H2 and Cl2. So that is 131 and 223 minus 2 times the entropy of HCl. So that's 2 times 187. So what is the entropy change here? Minus 20 or negative 20 joules per Kelvin per mole. The delta H for this reaction is plus 185 kilojoules per mole. Calculate the standard Gibbs free energy change. Now we know that delta G is equal to delta H minus T delta S, right? We want to calculate this at 298 Kelvin. So we have delta H is 185 minus the temperature, which is 298. And we want to calculate in kilojoules per mole. So we convert the entropy change, right? That's minus 20 into kilojoules. So that will be divided by 1000. So then what does the Gibbs free energy change come out to? So the 3 significant figures, we get the Gibbs free energy change is 191 kilojoules per mole. Okay. Predict the effect of increasing the temperature on the spontaneity of this reaction. Now, this entire term, this minus T delta S term, this minus T delta S is a positive value, right? You have a minus and a minus. Minus and a minus. So this is a positive value. So if I increase the temperature, what happens to this value? It becomes more positive. If I increase the temperature, this value becomes more positive. So what happens to the spontaneity if the delta G becomes more positive? Right? We can say over here that the spontaneity or feasibility, right? Feasibility or spontaneity decreases. Okay? Because why? T delta S is negative. Therefore, minus T delta S is positive and becomes more positive. And or we can say that minus T delta S and delta G becomes more positive if temperature increases. Next question that we have here is question number 4. Separate samples of 0.01 moles of magnesium nitrate and 0.01 moles of strontium nitrate are heated until completely decomposed to the metal oxide, nitrogen dioxide, and oxygen. State which of these two 2 nitrates requires the higher temperature before it begins to decompose. So which is more thermally stable? We know the thermal stability increases down the group, right? Thermal stability increases down the group. So that means over here that strontium nitrate will require the higher temperature, right? And the reason why is because the Sr2 plus ion, right, has a greater radius, obviously lesser charge density, right? And therefore lower charge density than the Mg2 plus ion, right? Meaning that it has a, we can say therefore it has a weaker polarizing effect, or, right, it has lesser polarizing power and does not polarize the anion as much, and does not polarize the nitrate ion as much, or distort the nitrate ion as much, right? The greater the polarization on the nitrate ion, right, the more easily it will decompose, the less thermally stable it will be. Okay. After decomposition is complete, the 0.01 mole sample of magnesium oxide is taken and increasing amounts of water are added to it with stirring until no solid remains. This procedure is repeated with the 0.01 mole sample of strontium oxide. Identify the sample to which most water must be added to cause all the solid to dissolve. Explain your answer by reference to the solubilities of the products when water is added to the oxides. You should refer to relevant energy terms in your answer. So strontium oxide versus magnesium oxide. To which must more water be added? So which is less soluble is what the question is asking. Right? We know that the solubility of the hydroxides increases down the group. We know magnesium oxide is barely soluble. So more water will be added to magnesium oxide. Magnesium oxide. Okay. The reason why is because we can say over here, because magnesium hydroxide, right, is less soluble than strontium hydroxide. And the reason why is since the delta H solution is more endothermic for magnesium hydroxide. What happens down the group? Down the group, both delta H lattice and delta H hydration become less exothermic. But when solubility is decreasing down the group or increasing down the group, that means that hydration stays more exothermic. So lattice enthalpy changes by a bigger factor. Okay. So we can say, but the change in the lattice enthalpy is greater. The nitrogen dioxide given off by the decomposition of 0.01 moles of strontium nitrate is dissolved in water. The oxidizing agent H2O2 is then added to give 150 cm cube solution with nitric acid as the only nitrogen containing compound. Calculate the concentration in moles per dm cube of HNO3 in 150 cm cube of solution. Now the idea here is that H2O2 is oxidizing the nitrogen dioxide, right, where nitrogen has an oxidation number of +4, to HNO3 where nitrogen has an oxidation number of +5. Now rather than writing an equation, the simplest way to do it, right, is simply to say over here, what we have is, right, you have NO2 plus H2O2, right, to form HNO3, right? And what we have over here is we're going to have just 2 moles of HNO3, right? Now, and we have 2 NO2 over here, right? Now, even if you're unable to construct this equation, what you should be able to identify is that for every 1 mole of nitrogen dioxide, you're going to produce how many moles of nitric acid? 1 mole, right? These will always be in a 1:1 ratio, since the nitrogen atoms can only come from one place. So even if you're unable to construct this equation, you should know that if you have 0.01 moles of strontium nitrate, right, what do you have? You have this as your equation. So if you have 0.01 moles of strontium nitrate, how many moles of nitrogen dioxide will be produced? We know that if we have 0.01 moles of this, right, 0.02 moles of nitrogen dioxide will be produced. So if you have 0.02 moles of nitrogen dioxide, then how many moles of nitric acid must be being produced? 0.02 moles. Again, if you can't construct the equation, it doesn't matter, it's fine. Even if you know the molar ratio of nitrogen dioxide and nitric acid, that would be acceptable, okay? So over here, what we have is, we have 0.02 moles of nitric acid. So then what's the concentration? The number of moles per unit volume. So that will be 0.02 divided by the volume in decimeter cube. So that will be 0.15. So then what does this concentration come out to? This is equal to 0.133 moles per decimeter cube. So that's your answer. Okay. There we go. The HNO3 present in 25 cm cube of this solution is neutralized using 0.125 mole per decimeter cube NaOH aqueous. Calculate the minimum volume in centimeter cube of NaOH aqueous needed. Give your answer to 3 significant figures. So over here, what we have is we have HNO3 reacting with NaOH to form sodium nitrate and water, right? It's a neutralization reaction. And what we have over here is, we know that the number of moles of this is 0.133, right? That was the concentration multiplied by the volume, which is 25 centimeter cube. So that's 25 divided by 1,000 decimeter cube. So then what does this volume come out to? Or what does the number of moles come out to over here? So we have 0.003325 moles. So then that's obviously the same as the number of moles of NaOH. So for NaOH, we can say the number of moles, that 0.003325, is equal to the concentration, that's 0.125 times the volume, right? And we want it in centimeter cube, so let's just divide by 1,000 here. So what does that volume come out to? We get 3.325 divided by 0.125. The volume over here is 26.7 centimeter cube. Next question that we have is question number 5. Transition elements form complexes. Molybdenum forms an octahedral complex consisting of one MO atom surrounded by carbon monoxide molecules. CO is a monodentate ligand. Iron forms an octahedral complex consisting of one Fe3+ and a number of cyanide or Cn- ions. And again, Cn- is a monodentate ligand. Define the term monodentate ligand. Okay, it is a species that donates one lone pair of electron to form one dative bond to a central metal atom or ion. Okay. Complete the table by stating the formula and the charges of the complexes described. Now, in molybdenum, you have a molybdenum atom followed by, if it's an octahedral complex, how many monodentate ligands do we have in an octahedral complex? It'll be 6. It'll be 6 monodentate ligands, right? Octahedral is a 6 coordinate shape. So we have MoCO6. The MO atom is also neutral and carbon monoxide is also neutral. So the charge is just 0, right? And for iron 3, you have 6 cyanide ions. You'll have FeCN6, but the charge over here would be 3 minus. Okay. So obviously, if you were to write the charges over here, this would look like this. Yeah. Okay. You don't have to put the square brackets for the neutral complexes. Draw a 3-dimensional diagram to show the shape of this iron 3 complex. So over here you have an octahedral complex with 6 cyanide ions, right? So what you have is this guy over here, this guy over here, and then this guy over here, right? So you have a CN, a CN, a CN. Make sure you show the carbon bonded to the iron, not the nitrogen, right? And this has a 3 minus charge. An excess of aqueous ammonia is added to dilute copper 2 sulfate solution. A dark blue complex is formed. Write an equation for this reaction, an ionic equation for this reaction. So what you have is, if you look at just the ionic equation for this reaction, what you have over here is an aqueous solution. You have CuH2O 6 2 plus. Okay, in the previous part we also had to label 180-degree bond angle. So over here that's what the label would look like. Right, this is what the label would look like. Okay, just show a bond angle between two opposite ligands. Okay. Now for the ionic equation, you have aqueous copper sulfate, so you have CuH2O6 2 plus, right? And it's reacting with 4 ammonias to form Cu NH3 4 times, right? You have 4 of those. H2O twice. Right, and again this is a 2 plus complex, and we have 4 H2O released. All right. Explain the origin of color in copper 2 complexes. So here, I'm just going to write this in bullet points, okay? But this is a very common question in the exam. What happens is that the d orbitals are split, right, into two different sets, right, with different energies, or you can say into non-degenerate orbitals, right? Different energies or energy, right? The delta E corresponds, or the difference in energy between these two levels corresponds to a frequency of visible light, right, that is absorbed. And when that frequency of visible light is absorbed, right, electron is promoted or excited from lower energy to higher energy, d orbital, right? And lastly, the complementary color is observed, right? Whatever frequency is absorbed, you have white light, so whatever frequency is absorbed, the remaining color is observed. So complementary color is observed. An excess of concentrated hydrochloric acid is added to the dark blue solution of this dark blue solution with the copper amine and water complex, right? A new complex Z is formed. The color of the solution changes. Write an equation for the formation of Z from the solution, from this dark blue solution. Include the formula and charge of Z. So over here, when you add chloride to this solution, what you end up making over here is this. You have Cu NH3 4 times and H2O twice, right? And with chloride, you make a tetrahedral complex. So you're going to have 4 chlorides, okay? Or you can say, you can also say HCl over here. So if you have HCl over here, for example, right, then you would form CuCl4 2 minus, okay, plus, again, you're going to have 4 HCls, right? Since you have 4 chloride ions, you're going to form this. Then you're going to form 2H2O, and you're going to form 4 NH4 plus, because the ammonia will react with the H pluses. You can also just say CuCl4 2 minus plus 2H2O, right? Plus 4 NH3 if you don't write H plus. So if you just wrote 4 Cl minus, right, then you would have 4 NH3 here. So you can write the ionic equation, or you can write HCl. You can write Cl minus or HCl, okay? Name the type of reaction. What's the type of reaction over here? This is a ligand exchange reaction, okay? The geometry of Z, remember, it's a tetrahedral complex, copper chloride, okay? The color, it's a yellow solution, okay? Copper chloride, you should just remember these. Explain why the color is different from the color of this solution Z. So why do these two complexes have different colors? The reason they have different colors is because the difference in energy between the d orbitals is different in these two different complexes. So if the difference in energies is different, that means different frequencies of visible light are absorbed, so different colors will be observed. The next question that we have is question number 6. An excess of aqueous ammonia is added to a solution containing the complex ion cobalt hexaaqua, right? Cobalt 2 hexaaqua. Complete the sentence to describe the color change that will be seen during this reaction. The color changes from aqueous cobalt is a pink solution, okay? So it changes from pink to, with hexaamine, right, the ammonia wala solution is a brown solution. So it's pink to brown, okay? You can also say pink to yellow or straw color. Just stick to brown. It's an easy color to remember, okay? Write an expression for the stability constant. The stability constant over here would look like, CO NH3 6 2 plus, right? That's the product divided by the concentration of the reactants, which are NH3 to the power of 6, and you have CO H2O 6 2 plus. The numerical value of K stability for the hexamine complex is 7.7 times 10 to the power of 4. What deductions can be made about the hexaamine and the hexaaqua complex from this K stab value? So this is around 77,000. So what does that tell you? Which complex is more stable? Which is in much higher concentrations? Is it the hexaamine or the hexaaqua complex? Right? The numerator is much larger. That means this complex is going to be in much higher concentrations. So therefore we can say over here that the CO NH3 6 2 plus complex is more stable than the hexaaqua complex, okay? Oxygen can oxidize CONH3 2 plus to CONH3 3 plus under standard conditions in alkaline solutions. Use this information and the data booklet to calculate the E0 cell value for this oxidation of cobalt 2 hexaamine. So for alkaline conditions, we're going to use this half equation, right? Oxygen is the oxidizing agent, so it's undergoing reduction. And they've given us the standard half equation for cobalt 3 hexamine to cobalt 2. Now, obviously, our reactant over here is CONH3, CONH3 6 2 plus, right? So we're just going to reverse this equation over here. So we have a plus 0.4 for the oxygen, right? And if we just balance the equation on top, right, we're going to write the reverse equation for this. So we're going to have an E naught of minus 0.1 for the reverse equation, right? Because our reactant is the 2 plus, right? So that guy is undergoing oxidation, so it will lose electrons. So we have a minus 0.10 volts here. So therefore, we're going to have the E naught as 0.30 volts, okay? This is the equation that we're looking at. So what you have over here is, this is your half equation for the oxidation of the cobalt 2 complex to the cobalt 3 complex. Okay, so you have 4CO NH3 6 3 plus 4 electrons. Okay, and again, the other half if you have aqueous conditions, then you're going to use the other half equation. That's the plus 1.23 volt. Okay, but in alkaline conditions, you'll have hydroxide ions present, so you're going to use this one. Okay, for aqueous solution, you're going to use the other one. Write an ionic equation for this oxidation of CONH3 6 2 plus. So for the ionic equation over here, what you have is, just add up these two equations together. So what you end up with is, you have 4 CO NH3 6, right, 2 plus O2 plus 2H2O. Those are your reactants, right? The electrons obviously balance each other out, and then you're left with 4 CO NH3 6 3 plus and 4 OH minus. The last part says, predict by selecting suitable data from the data booklet whether oxygen can oxidize CO2 plus in acidic solution in the absence of ammonia. So in acidic or an alkaline solution, in acidic or a neutral solution, we have the following half equation. So here we have the following half equations. Okay, this is the half equation for oxygen in acidic conditions or neutral conditions. Okay, this was the one for alkaline conditions. This is for neutral or acidic conditions. That's plus 1.23. And we want to know if we can oxidize cobalt 2 plus to cobalt 3 plus. So what we have is CO2 plus to form CO3 plus, right, plus an electron. This has an E naught of negative 1.82, right? And we're using oxygen as the oxidizing agent, so it'll undergo reduction. That's plus 1.23. So for oxygen, we'll have an E naught of plus 1.23. So will this reaction occur? Over here? They're saying in the absence of ammonia, so just regular cobalt, if you had aqueous, that would be negative 1.82, right? And for oxygen, it will be positive 1.23. So this reaction won't occur, okay? So we would say over here, no. And write down these two half equations as well, okay? We have O2 plus 4H plus 4 electrons, right, giving you 2H2O. So you would say over here, no, because the E naught of the cell is equal to negative 0.59 volts. So that's a negative E naught. So that means that the reaction will be non-spontaneous. So it won't occur. Okay. The structure of benzene 1,3-dicarboxylic acid is shown. So here we have benzene 1,3-dicarboxylic acid. State the empirical formula of benzene 1,3-dicarboxylic acid. Now for the empirical formula, first let's just figure out how many carbons we have. We have 6 in this ring and then 7, 8. So we have C8. Right? How many hydrogens do we have? 4 on the ring and then 5, and then 6. So we have H6, and then we have 4 oxygen, so O4. So what's the empirical formula here? The empirical formula here would be C4H3O2. Benzene 1,3-dicarboxylic acid is an isomer of benzene 1,4-dicarboxylic acid. These two isomers can be distinguished by carbon-13 NMR spectroscopy. State the number of peaks in the carbon-13 NMR spectrum of each compound. So if you look at benzene 1,4-dicarboxylic acid, right, this is what it would look like. We have a CO2H here and a CO2H over here. Now, right at the 1 and 4 position. Now, first of all, if you look at benzene 1,3-dicarboxylic acid, how many peaks will show up in the carbon-13 NMR spectrum? Now, what we see over here is, first, let's just look at the two carboxyl groups, right? These two are identical carbons. If you look at this carboxyl group or this carboxyl group, the molecule looks identical from either perspective. So what we have is, this is one carbon atom, right? Then the one in between is two carbon atoms. The one that they're bonded to, right? Those are also identical. That's 3. Then the ones next to them, right, on the other side, that's 4. And then one over here. So that's 5 different types of carbon atoms. There's obviously a line of symmetry here. There's a line of symmetry here. So we have 5 different carbon atoms over here. And what about benzene 1,4-dicarboxylic acid? Now again, both the acids are identical, right? The carbon that the acids are bonded to are also identical, right? Now what about these remaining 4 carbon atoms? Are they different in any way, or are they all the same? They're all the same, right? They're identical. There's 2 lines of symmetry here. So this is just the third type of carbon atom. These 4 are all identical. So we have a total of 3 different peaks for benzene 1,4-dicarboxylic acid. Benzene 1,3-dicarboxylic acid can be made by the 2-step synthesis shown below. In step 1, what we do is we take this compound P, right, which is benzoic acid, and we make compound Q. So first we have to name compound P. Compound P over here is simply benzoic acid. Compound P is simply benzoic acid. Explain why the major product of this 2-step synthesis is benzene 1,3-dicarboxylic acid and not benzene 1,4-dicarboxylic acid. So over here, if you guys remember, the carboxyl group is a 3,5 directing group, or it's a 3 directing group. So because the carboxyl group is already present on the benzene ring, any incoming substituents will go on carbon number 3 and not on carbons 2 or 4. So we can say over here that CO2H is a 3 directing group. Next part. The reagents used for step 1 are CH3COCl and AlCl3. These reagents give rise to these ions over here, which react with compound P. Name the mechanism for this reaction. So what mechanism is this when you have substitution taking place on the benzene ring? This is electrophilic substitution, right? So we have electrophilic substitution. Draw the mechanism of this reaction with compound P. Include all relevant curly arrows and charges, the structure of the intermediate and the structure of compound Q. Okay, so now what happens over here is this. What happens over here is, first of all, in electrophilic substitution, the electrons go from the ring to the positively charged carbon, right? You have this positively charged electrophile. So let me draw this curly arrow like that, right? And you end up making this intermediate over here. And again, make sure that in the intermediate, we show the substitution taking place on carbon number 3, right? So what we have over here is something like this. We have this carbocation intermediate, right? We have a CO2H here, and we have this intermediate where you have the hydrogen atom and you have the COCH3. Remember, this is the carbon that bonds to the benzene ring on position number 3. And then in the second step, the electrons from the CH bond on the benzene ring go back into the ring and the CH bond breaks. So our final product over here looks like this. You can draw the skeletal formula, or you don't have to draw the skeletal formula, and then you have a COCH3. So in the next step, they're saying, suggest a reagent and conditions to convert compound Q into benzene 1,3-dicarboxylic acid in step 2. So what we want to do is, we want to convert this guy. We have a methyl ketone here, and we want to break this CH3 off, and we want to convert this into a carboxylic acid. So for that, if you remember, we have a CH3CO group. We have a CH3CO group. And for this reaction, what we use is, we use alkaline aqueous iodine. We break this and we end up making this guy, right? So for that, we're going to use alkaline aqueous iodine. All right. So the reagents over here are alkaline aqueous iodine, alkaline iodine aqueous, or you can say iodine aqueous and hydroxide ions. And then you're going to followed by H plus. The reason you want to follow it by H plus is because then you want to convert the salt of the carboxylic acid into a carboxylic acid group. So when you add H plus, that salt will get converted into a carboxylic acid. Next question that we have over here is question number 8. Alanine and glutamic acid are two naturally occurring amino acids. This guy over here, which is alanine, exists as two optical isomers. Draw three-dimensional structures of these two optical isomers. So here we just have to draw the two enantiomers. So first identify the chiral center. This is our chiral center over here. So we have a carbon atom that is bonded to a CO2H. It's bonded to a CH3. It's bonded to an NH2, and it's bonded to a hydrogen atom. Okay, and if you look at the mirror image, right, the CO2H obviously stays on top. Over here, whatever's closer to the mirror plane will appear closer in the mirror image as well. So we have a CH3 here. Then we have an NH2. And then we have a hydrogen atom, right? And if you want, we can just label that chiral center for good measure over here, right? So these are your two optical isomers. And I'll also just draw the mirror plane as well. Okay, this is your mirror plane. The proton NMR spectrum of either alanine in D2O or glutamic acid in D2O is shown. State whether this is the spectrum of alanine or the spectrum of glutamic acid. Explain your answer by reference to the number of peaks and the splitting patterns. So first of all, let's actually look at the two structures that we have over here. We have glutamic acid, right? And we have alanine. And we have alanine over here. So I'm just going to look at their two structures over here, right? And we have to figure out which of these two compounds does the NMR spectrum belong to. Okay, I have to figure out which of these two does the NMR spectrum belong to. Now the first question that I have over here is that which peaks will disappear when I add D2O? Which peaks will disappear for both or for either of them when I add D2O, right? We know that any protons that are bonded to either a nitrogen or a hydrogen or an oxygen will disappear, right? Any OH peaks and NH2 peaks, any OH or NH peaks will disappear. So these two peaks won't show up on the, or over here in glutamic acid, these three peaks wouldn't show up, and in alanine, these two peaks wouldn't show up, right? Because these are OH or NH peaks. Now we have to figure out whether this is the spectrum for alanine or glutamic acid. Now just by looking, how many different types of protons do I have in this spectrum? Excluding the NH and OH peaks. How many different types of protons do I have? I have two different types of protons, right? I have two different types of protons, and I have a doublet and a quartet. So which one do you think it belongs to? Which of these two, alanine or glutamic acid, have two different types of protons? Only alanine has two different types of protons, right? You have a CH and a CH3. So over here, the CH, let's call that HA, is split into a quartet by the neighboring carbon's 3 protons. So this is HA, right? And the CH3, right? You have 3 protons here. Let's call that HB, and it's split into a doublet by the neighboring carbon's 1 proton. Remember, this is the n+1 rule. If the neighboring carbon has 3 protons, you'll get a quartet, right? You'll get 4 peaks. And for this guy, HB, the neighboring carbon has 1 proton, so you'll get a doublet. So over here, you have 2 different protons, and you see that doublet quartet pattern. Whereas for glutamic acid, you actually have 1, 2, 3 different types of protons. So you would actually see 3 peaks in this spectrum, okay, excluding the OH and NH peaks. So over here, we would say that this spectrum belongs to alanine, okay? And we have to refer to the number of peaks and the splitting patterns. So it's alanine, okay, because it has 2 different types of protons. It has 2 different types of protons. Right? Hence 2 peaks. Okay. Whereas glutamic acid has 3. Right? And this is obviously excluding, the NH and OH peaks, right? And the next thing over here, we have to refer to the splitting pattern, right? So if we have to refer to the splitting pattern over here is that the CH proton is split into a quartet, okay, by the neighboring CH3, right? And the CH3 protons, right? The CH3 protons are split into a doublet by the neighboring CH. The mass spectrum of glutamic acid is obtained. State the mass to charge value of the molecular ion peak in this spectrum. So that's the M peak. So if you calculate the molecular mass for this guy, assuming, okay, obviously all the carbons are going to be 12, nitrogen is 14, and hydrogen is 1, right? And oxygen is 16. If you calculate the MR of this guy, the MR comes out to 147. So that will be the value of the mass to charge ratio on the M peak. And obviously remember that in the molecular ion will be the 1 plus ion. So the charge is just +1. So the mass is just the molecular mass. So 147 divided by 1 will give you 147. The spectrum has peaks with mass to charge values of 88 and 131. Draw the structures of the ions responsible for these peaks. Now, first of all, if you look at the peak at 88, right, you have a molecule that has a mass of 47. Now, some fragment breaks off and you get a peak at 88. So what's the mass of the fragment that breaks off? What's the mass of the fragment that breaks off over here? 147 minus 88 would be 59. So what fragment do you think has a mass of 59? I'll give you a hint. When you talk about 59 over here, the CO2H has a mass of 45. CO2H has a mass of 45. So then, what could it be that has a mass of 59? We should have a CH2 CO2H. CH2 CO2H would be 45 plus 14. So that would have a mass of 59. That would have a mass of 59 over here. So when the CH2 CO2H breaks off, over here, what are we left with? We're left with NH2 CH, and then we have the CH2, one CH2 is still there, but the other CH2 CO2H is broken off. So you have a CH2 and then you have a CO2H. And again, this will be a 1 plus ion. Again, the 59 over here is what has broken off, leaving you with 88. It's easier to reduce the 59 than the 88. So we actually first just determine what would break off to leave you with a mass of 88. If you have a total mass of 147, if 59 breaks off, you're left with a mass of 88. So what breaks off? The CH2CO2H breaks off, leaving you behind with this structure. Again, you can figure out directly what fragment has a mass of 88, but it's actually easier to determine what broke off in this case, and then figure out what's left behind. All right. The next fragment over here has a mass of 131, right? So if it has a mass of 131, what broke off to leave you with a mass of 131? Whatever broke off had a mass of 16. So what over here do you think has a mass of 16? Right? The NH2. If the NH2 breaks off, right, NH2 nitrogen has a mass of 14 and then 2 hydrogens are 16. So if the NH2 breaks off, right, what are you left with? You're left with this entire thing over here. What you're left with over here is a CH, right? The NH2 is broken off. Then you have a CH2, CH2, CO2H, right? And then you have a CO2H. And this has a mass of 1 plus again. All right. At pH 11, alanine exists as this particular ion. You have an NH2CH, CH3, CO2 minus. So you have a pH above the isoelectric point. So what happens is that the acid loses its proton. Okay? And glutamic acid exists as this 2 minus ion. Both the acids lose their protons, right? A mixture of alanine and glutamic acid at pH 11 is subjected to electrophoresis. State how the mixture can be maintained at pH 11 during electrophoresis. So what would you use to maintain the pH or to ensure that the pH doesn't change too much? We would use a buffer solution. Draw a fully labeled diagram for the apparatus that would be used to carry out this electrophoresis. Your diagram should include the position of the mixture of alanine and glutamic acid at the start of the electrophoresis experiment. So the very simple experimental setup for this would look like this, okay, for electrophoresis. What you have is you have a container, okay, what you have over here is you have a container, okay, and the container is filled with gel, okay, or you can use a paper. We're just going to use a gel over here, okay, and what we're going to do is we're going to place a sample of amino acids in the middle. Right? So here are amino acids placed in the middle, right? And what you have is you have these plates, okay, these metal plates on either side that are connected to a power source. So you have the positive terminal and the negative terminal over here. Okay, you have the positive terminal and the negative terminal over here. And what will happen is, since you have negatively charged amino acids, which terminal do you think they'll move towards? Since both of these amino acids are negatively charged, they're going to move towards the anode. Okay, so this is the anode. That's the positive terminal, and then you have the cathode over here. That's the negative terminal, and let's also label the power source over here. Right, this is our power source. You have a DC supply of current over here. Okay. And again, because this gel conducts electricity, we have a positive and negative terminal, so the negatively charged amino acids will move towards the positive terminal. The extent to which they move towards the terminals depends on the charge of the amino acids as well as the mass. The heavier the amino acid, the slower it will move. The heavier the amino acid, the slower it will move. The greater the charge, the faster it will move. Okay. And obviously the charge, if you add positive amino acids, they would move towards the cathode. Okay. Their position at the start is the center position. No? I just labeled it here. Right. Amino acids, that's your sample. Identify the electrode to which that each amino acid travels towards during electrophoresis at pH 11. They're both negatively charged, so they'll both travel towards the anode, which is the positive terminal. In a particular electrophoresis experiment at pH 11, the glutamic acid travels 3.4 centimeters and alanine travels a shorter distance. Explain the factors that account for the difference in the distances traveled. So over here, which one is heavier? Which one is heavier over here? Glutamic acid is heavier, but even then it's traveling a greater distance. So what factor is playing a bigger role in the distance they travel towards the anode? Is it the charge that's playing a bigger role or the mass? This is a larger molecule, but it still travels a greater distance. That means that the mass isn't playing as much a role as the charge over here. Okay. So again, the question is saying explain the factors that account for the difference in the distances traveled. So the idea here is that even though alanine has a lower MR, right? It travels a shorter distance, right? It travels a shorter distance than glutamic acid, okay? Because the charge on alanine is -1, whereas on glutamic acid it is -2. It is -2. Okay, and you have to mention both things. You have to mention the mass as well as the charge, since the question is asking for the factors that account for the differences. Okay, so generally speaking, they're both factors that affect it, but in this case, the MR is not as deterministic as the charges. The next question that we have over here is question number 9. Question number 9 says butylamine can be synthesized from different organic compounds by using suitable reagents. Each reaction involves one step. Complete the table to describe 3 different syntheses. One of the 3 syntheses should involve a nucleophilic substitution reaction. The starting organic compound for each synthesis should contain a different functional group. A different reagent should be used for each synthesis. So let's start with the first condition. What type of a compound can be converted into an amine using nucleophilic substitution? So if you guys remember, we can take a halogenoalkane and react it with ammonia, right, under pressure or heated in a sealed tube. And we can convert the halogenoalkane to an amine. So for example, if I started with, let's say, bromobutane, right? If I start with bromobutane, or 1-bromobutane rather, I should say, right? What do I get? Right, this guy Br, right? And I react this with ammonia, okay, under pressure, okay, or I can say heat in a sealed tube, okay. The reason we're heating in a sealed tube is because we need to heat under pressure. Okay. Then I will end up making an amine. This is nucleophilic substitution of halogenoalkanes. Now someone mentioned that we can also reduce nitriles to form butylamine, and that is true. We can use a nitrile, so something like CH3. We can use something like butane nitrile, right? So if we have butane nitrile over here, we have CH3, CH2, CH2, and then we have a C triple bond N. And if we reduce that nitrile, okay, by using hydrogen and nickel catalyst and heat, right, we can convert that nitrile into an amine. Here you can also use lithium aluminum hydride as your reducing agent. Okay. What's one last compound that I can use to make an amine from some other starting compound? I can start with an amide, right? Okay. And if I reduce an amide, for example, right? And for that, I can use a different reagent. For reducing an amide, right? So if I have something like this, and then I have a CO and H2, that's an amide linkage. And if I reduce that amide using lithium aluminum hydride, okay, in dry ether, or I can say anhydrous lithium aluminum hydride and heat, I can reduce that amide to form an amine. So I have over here satisfied all these conditions, right? We have a nucleophilic substitution reaction. Starting compound contains a different functional group. We have a bromo bromo group here, nitrile here, and amide here, and a different reagent has been used for each synthesis. Compare and explain the relative basicities of ammonia, butylamine, and phenylamine. Now, which of these is the most basic? So, for example, if I have ammonia and I can compare it to butylamine, if I compare it to butylamine, which of these is more basic? Right, butylamine is more basic. The reason why is because of the electron donating effect of the alkyl groups, right? The electron donating effect of the alkyl groups, which means that the charge density on the nitrogen increases, right? It's more likely to donate its lone pair and accept a proton, right? Positive inductive effect of the alkyl group, right? And what about ammonia versus phenylamine? Then which is more basic over here, if you guys remember? Phenylamine is this guy, right? In phenylamine, it's the opposite, right? The delocalization of the lone pair into the benzene ring means that these electrons are less likely to be donated and accept a proton. So phenylamine would be the least basic and butylamine would be the most basic, okay? So we have butylamine followed by ammonia, okay, followed by phenylamine, okay? So the idea here is that butylamine is the most basic, okay, due to the electron donating effect of the alkyl group, right? Making the lone pair, right? Making the lone pair more reactive or increasing the negative charge. So you can say making the lone pair, right, more likely to be donated. Right, more likely to be donated, and obviously for N to accept a proton. Okay. On the other hand, phenylamine is the weakest. Phenylamine, okay, is a weaker base than ammonia due to the delocalization of the lone pair into the benzene ring, okay, making it less available for donation, or less likely to be donated, okay, and accept a proton. And over here, obviously, you can specify that the lone pair on the nitrogen, right, into the benzene ring, making it less available for donation. The next question that we have over here is question number 10. Complete the table to show the structure of the organic product from each reaction of phenol. Okay, now when phenol reacts with NaOH, what type of a reaction do we have here? Phenol is acidic, so it reacts with NaOH to form a salt and water, right? It's an acid-base reaction. So in this case, you're going to form sodium phenoxide, right? You're going to form sodium phenoxide. The phenol will lose its proton, right? And you'll end up making this compound. What about phenol and sodium? Again, phenol is acidic. So if you guys remember, it has an OH group as well. So again, it will form salt and hydrogen gas. So the organic product will again be sodium phenoxide, right? You're going to form the same salt here as well with sodium, right? Phenol with this diazonium salt over here and NaOH at 4 degrees Celsius. What type of a reaction is this? You're going to make an azo dye, right? So what will that look like? Let's say you have the phenol here. Then what will happen is you're going to make this azo dye linkage over here, right? And then you have this benzene ring. So you've made an azo die over here, okay? And the last one is if you have an acyl chloride reacting with phenol. For the first two, you can also write just the anion as well, okay? Now in the last one, phenol reacting with an acyl chloride will give you an ester, okay? But over here, I would like to point out that they haven't mentioned one particular condition for esterification of phenols. Now over here, even though you're going to draw the ester, do keep in mind that for phenol to esterify, if they asked you to quote the conditions, you should say alkaline conditions, okay? So first phenol makes the phenoxide ion, then it esterifies with an acyl chloride, okay? So that would be the more accurate conditions over here. And what we have over here is we have this diester form, right? You have a C double bond O over here that forms an ester with this phenol, right? And you have the C double bond O over here that forms an ester with another phenol here. All right, identify two reactions from the table in which ethanol would behave in a similar way to phenol. So in which two reactions with ethanol would behave in a similar way to phenol? Ethanol has an OH group, so it will react with sodium, and ethanol can also form esters. Okay, so it will be 2 and 4. It won't react with NaOH. Ethanol is not acidic. Okay, and it obviously won't do a coupling reaction either with the diazonium salt. Okay, so the two reactions over here are reactions 2 and 4.